Greetings for the day. This is paper ID number 7, presented by H. Mary Henrietta. Our title of the manuscript is A Robust Self-Generating ANFIS Training Algorithm for Time Series and Non-Time Series Intended for Nonlinear Optimization. Let's get on to the presentation. First, let's have the outline of the presentation. So first, we're going to start with the introduction and then move on to ANFIS algorithm development, flowchart, the EOQ model and the groundwater level, and finally the conclusion. So first let's start with the introduction. So this research enables the ANFIS to test the data using an artificial training database generated by the given algorithm. The Gaussian membership function is given down in this EOQ model to forecast the outcome. ANFIS will put the data to the test using an algorithm-generated artificial training database. There is a clear correlation between performance and output data in the ANFIS algorithm. So the development of the algorithm. Towards my right side, the figure shows the Gaussian membership function which is being implemented for the algorithm. So the algorithm is built on a database of self-teaching. So this system examines the definition of the parameters such as high, low, etc. So the technique generates performance data using random permissions after examining all of the statistical variables from the input data. So every loop, what we see here, generates a new set of production data. The user must change the quantity of duplicate items to receive a big amount of transaction data. So when the user increases, the values get repeated and the memories provided by the system is used to train for the data. And if the number of epochs just gets continued, the system becomes unstable. So here is the flow chart for the EOQ model. So EOQ model will be non-time series. So the expansion of EOQ is economic order quantity. So economic order quantity, in other words, we see it's as called as the optimal order quantity. That is the amount of order we are intended to do it for a inventory system. So here the input data for the EOQ model is given and it generates the synthetic data required to train the ANFIS. So when it trains, the test data is validated and we check the model with the crisp data, we compare it. And if it's yes, it reaches the permissible limit. If it's no, the process is ended. It just keeps going. And now let's have the non-time series, that is the EOQ model. The optimal quantity in the crisp model is derived as Q is equal to 2 times of O of C minus PR, where UH. So here, this towards my left, it's the training data set with the number of iterations involved to compare with the crisp output and ANFIS output. And towards my right, we have the comparative analysis for the EOQ model with the actual output, ANFIS output, and fuzzified output. And now the groundwater level. The groundwater level is everywhere we study about it. It gets decreased due to the less amount of rainfall. There are a lot of studies based on groundwater level. It is based on the time series because as time moves on, the groundwater level fluctuates. So there are two graphs here, and towards my left is the tested number of data sets for the groundwater level. The actual output is given in color red, and ANFIS output and fuzzified output is being studied under numerous data sets. And towards my right is the comparative analysis of the groundwater level with actual output, ANFIS output, and fuzzified output. So let's move on to the conclusion. So the conclusion starts with an integrated platform for neural networks, fuzzy logic, and neurofuzzy networks can be used to create a variety of hybrid systems. The abstract notion, for example, you can be using the mixed findings for several neural networks for any sort of applications we have, for any hybrid systems that are developed, and the current work has been produced, and we have promising results out of the neural networks working. The field validation shows that this approach has been a promising prospect in measuring a wide range of online issues. So what will be the advantages of all this? It includes the ability to erase errors and sounds in the data, which is very much important for us. And if the data is lost between two data points, it can also be included depending on the standard deviation and trend. This procedure can be followed in a number of ways. The data for the training is expandable because data sets can move between the maximum and minimum of actual data, and directly we can forecast the results, even if the data is out of line. So using this approach to improve the performance data makes it clear the ANFIS system to determine the output. So here, when we change the data groups of membership actions, the time is expensive, as everyone knows it, and we can forecast the immediate outcome after defalsification. And these are my references. We have applied around 25 references, and these are the very few in a nutshell. Thank you so much.